Alright guys, welcome to the next video on spectroscopy. This one is going to be going over mass spec, and it's going to be the last thing you guys learned for your exam 2. Alright, so again I wrote 2 examples here. Both of these are from your workshop, and then I'm going to go over one example from exam 3 of 2018 after these 2, okay? Alright, so let's get into it. So the way that mass spec works, right? Here, I'll start using the original example to help explain how mass spec works. So what mass spec does is it shoots an electron at the compound that we start with, right? And it's going to create a radical and a cation, all right? So what it's going to do is imagine it shoots that bond, which has 2 electrons, and remember there's a carbon right there, and it's going to knock one out. So remember, a bond requires 2 electrons. So if I knock one out, we broke the bond. So what I'm going to do is imagine this bond splits now, so I have a CH3, and I have this carbon. That means because we still had 1 electron, right, we kicked 1 out, so here's our E minus, plus the 1 that we used to shoot. So we still are left with 1 electron on a compound. One of these compounds gets a radical, whichever one you want. Other one gets a plus charge. Now I could have done the same thing and given this the radical, and this could get the plus charge. Okay, so what mass spec does is it can detect the cationic species. All right, it does not detect your radical, only the carbocation or the cationic species. All right, and so that's just something to keep in the back of your head, that the charged cation will be what is actually shown in this graph, not the radical. All right, and so this is how mass spec fragments. We can see how we generate the radical and the cation. Radical kind of goes away. Radical goes away, and we only look at the cation. So now I want to quickly analyze the pieces of the graph that's important. So the peak all the way to the right, that's called the parent peak. Okay. Now this peak right here, this is called the base peak, the highest peak. The base peak is going to be the cation that you generate that's the most abundant. In other words, it's the most stable cation you can form. The parent is the original peak, so it corresponds to here. All right. Now, I said that that's the rightmost peak, but if you look right there, we see a very tiny peak over there. That's if we have a carbon isotope, right? But we don't want to worry about that peak. What we're worrying about is the peak all the way to the right. That's the highest, like right there. Okay. So the strategy for this question is, so I cut it out actually on accident, but what they asked is they asked you to find the cation. What do you call it? The cation at the base peak, which was, if you look and count, 1, 2, 3, at 43. So your x-axis corresponds to the mass. All right, the y-axis corresponds to the abundance, which means the more abundant you are, the more stable. So they want you to find which of these structures, A, B, C, D, or E, corresponds to a mass of 43. All right, so the strategy for this is you take the parent peak, which is 72, and subtract the base peak. That's going to be 43. So you're going to get 29. That means from here to here, you lost a mass of 29, because I started with a compound at a mass of 72, and I dropped it to 43. So we lost that mass. So what you now want to do is you want to take your original compound and you want to cut it so that you can lose a mass of 29. All right. So right off the bat, what you could have done is you could see that, just to help verify for yourself, if you add up all the masses of every atom here, right, the oxygens, the carbons, and don't forget how there's hydrogens here, you would get a mass of 72. All right. And so now what we got to do is cut. So CH3, right, a carbon has a mass of 12, plus 3 hydrogens, which weigh a mass of 1 each. That's 15. So let's say I cut off a methyl, I would have only lost a mass of 15, right? So what I can do is, let's try to go one further, right? You're going to cut the ethyl group off. So you're gonna get instead is you're going to lose that carbon and 3 hydrogens, 15, plus another carbon, which would have been 12, right? So we're already going to be at 27, plus the 2 hydrogens with that ethyl, well, 29. Okay, awesome. We found our mass of 29. So let's just make some more room for ourselves here. So we found our mass of 29 to be that ethyl group. So the way we do this is, okay, we see that we want to split it where I drew that blue line. So do this. You can draw this 2 ways. I could put the carbocation here, and we get a radical on the ethyl. Or I could get the radical here, carbocation on the ethyl. Now they asked you for the cation at a mass of 43. So if you do this, that's the cation, that's the structure that you lost, the mass of 29. So we do not want to put the cation on there. That's not the fragment they're talking about. So we want to look at the top. All right, so now remember, I lost 2 carbons, 1, 2, 3, 4. That means I put the radical on the ethyl, one of the carbons, and I get a carbocation now on the carbonyl. So in mass spec, when we have a carbocation at that carbonyl, that's not the predominant form. So what's really going to happen is one of these double bonds is going to come down and resonate, and we're going to get this structure. Now, don't be confused here. A lot of students have confused this and asked me some questions that because they think that it's only 1 carbon when I draw it like this, and also there would be a plus charge here. That's 1 carbon. That's 2. So we still have those 2 carbons, one from the original carbonyl, and then the last one from the methyl. All right, this right here is called the acylium ion. So this is how carbonyls that had a carbocation directly on the carbon of the carbonyl actually look in a mass spec. So we knew that we lost the mass of 29, which is the ethyl. Got that there. So that means this has to correspond with the mass of 43. If you would have added up the oxygen, the 2 carbons, and the 3 hydrogens here, you would have seen that you would have hit the mass of 43. So all right, so that checks out. So that means that our answer here had to have been C. All right, so it's really all about a little bit of math in terms of doing some simple addition and then just corresponding what the mass that they're asking you to the masses at one of these structures. Okay, so let's do the same thing for the second one, but there's a couple of things we need to know first. All right, so I gave you an example with carbonyl in the beginning, but there's something else you need to watch out for, right? And that's going to be bromines or chlorines. All right, so you guys have to watch out for this. And why would you have to watch out for this? So it would be a good idea right now to pause this video and just go to Oscar and open up your exam 2 cover page. If you go to the Oscar homepage, not Oscar Folio, click exams, you'll see that it says exam 2 cover sheet and press the download button. You'll see that they give you masses and the abundance of various isotopes. This is going to help you and do a couple mass spec questions. All right. So why would this help us? So looking at the bromine and chlorine, I can see that they have 2 isotopes each. There's Br79, Br81. The 2 numbers at the top left of the isotopes are their masses. So you can see that the difference between these 2 is that they're a mass difference of 2 apart. And they have an abundance associated that they gave you also. This is about 51%. This is about 49%. Okay? So that's for the bromines. Now for the chlorines, we had a Cl35 and a Cl37. All right, again, look at them. The mass difference of 2 apart. And they also have an abundance. This one is about 75%, and this one was about 25%. Okay? So what's going to really help you out is the abundance in this case. So looking at our example here, look at these two peaks right here, the really high peaks. Okay? One of them is at a mass of 176. The other one is a mass of 178. So they're a distance of 2 apart. If we look at our isotopes, the chlorine has 2 isotopes 2 apart, and so does the bromine. Right? So just the fact that they're a mass difference of 2 apart won't tell us anything. But the abundance is what's going to help you. So if the BR79 and BR81, they're about 50-50 in terms of abundance. So what that means is if you have 2 peaks at relatively the same height, right? You can see that these are pretty much identical. The one on the left is just a tiny bit higher, right? That means we have bromine isotopes, okay? Because they're in equal abundance, either one of them would have been at the same height. So they would both be at the same height. Now the chlorine, right? This is 75 to 25%. So we had, let's change the color here. So we had this for the BR, right? For the chlorines, we would have had something like this. So this is 50, 50. This is 75, 25. Okay, you have a 1-to-3 ratio for chlorine, 1-to-1 ratio for bromine. So please watch out for those isotopes. There's a very good chance if they ask you a mass spec question, it's going to be something like one of these isotopes, and that's going to give you a hint. So you can see that we have 2 peaks relatively the same height, and with a mass difference of 2 apart. So that means we have bromines in our compound, a bromine. So anything without a bromine we can eliminate. So A, D, B, E. So now we're down to C and F. All right. So what they ask you in this question is to choose the structure that is the original compound. Okay. So we need a correspondent to our parent peak. Now remember, the parent peak is the one furthest to the right, but in a sense the larger one. So remember, in this case, this is our parent peak, right? Not this little peak right there. Okay. Same thing here. This is our parent peak, not that little one. Okay? So what we're going to do now is we're going to have to do a little bit of math. All right? So just adding this up. So we're trying to decide between C and F. The difference between C and F is that C has 2 hydrogens here, 2 hydrogens here. F has a double bond there. So it has 1 hydrogen there and 1 hydrogen there. So from C to F, you lost 2 hydrogens. All right? A hydrogen weighs 1 AMU, so we lost a mass of 2. Okay? So what you can do now, either using your calculator, but remember on the test you can use your calculator, right? You cannot. So if you use it here, just be careful that you can do this kind of math on test at a calculator, right? So if you add up the mass of C, right? Now, because Br has 2 isotopes, either one of them will work. If I pick the lower isotope, I am going to hit 176. Okay? If I hit the lower isotope, if that's what I use to add everything up. If I use the other isotope, the one that weighs more, you'll get this peak. Right? If you add up F, So let's say for the bromine, I used the smaller weight isotope, which was Br79. So what I'm going to do is I'm going to add up all that right now. So that's 12. We have 7 carbons, which weigh 12 each. So that's 84. So 7 carbons times 12, 84, plus 79 for the bromine. That's going to be 163. Plus, we're going to have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hydrogens. Right, so that's 163 plus 13. We're going to get 176. 176 perfectly hits that peak. If I use Br 81, that's just a mass of 2 higher, so I would get 178. So that matches up perfectly with our peaks. Now, if you want to check, you can do F. If I use Br79, the lower isotope, you would get a mass of 174 because there are 2 less hydrogens on F than C. So you can see that we don't even have 174 here. There is no peak at 174. They don't even give you anything below 175. Okay? Well, actually, no, below 176. So F cannot be our answer, and so we know that the answer now has to be C. So what I'm going to do is I'm going to go over exam 3 2018, the mass spec question there. Yeah, and so they give you our mass spec here, and they're asking you what corresponds to this structure. All right. So first thing you want to do, always see if you have any bromine or chlorine peaks. Right. The bromine is 1 to 1, chlorine is 3 to 1. Right. If you see over here on the right, I have these 2 peaks, a mass difference of 2 apart, roughly 50-50 in height. Instantly, we should be thinking we have a bromine. So we can eliminate anything without a bromine. Now we're down to E and F. So again, similar to IR, usually you can eliminate everything down to 2 choices for mass spec. So now what we want to do is, so it's asking you again for the original structure. We're going to have to do a little bit of math. Okay, so we want to find which of these structures, E or F, corresponds to 56 or 58, and you'll get either of them depending on if you pick the lower mass isotope or the higher mass. Up to you which one you want to use. So I'm going to pick using the lower mass isotope, so that's Br79. So 79, right, plus let's do E first. So it's going to be 79 plus 6 carbons, right, which weigh a mass of 12. 12 times 6, plus the hydrogens, so we have 1, 2, 3, 4, 5, and they weigh 1 each, so plus 5. So 79 plus 12 times 6 plus 5, we get 156. All right, look, we got that perfectly, 156. But let's try F, just to be on the safe side. So Br, again, let's pick 79, plus now 5 carbons. Oh, sorry, 6 carbons still, so it's 12 times 6, because it's the methyl now. And the amount of hydrogen. So we have 1, 2, 3, 4, 5, 6, 7 hydrogens. So plus 7. So if you do that, and then you do all the math out, what you're going to get is you're going to get a mass of 158. Oh, I actually messed up the math here. 1 second. Okay, no, never mind. The math was right, 158. So in this case, we're actually stuck, right? We got the mass of 156, yet we now hit the mass of 158 also. So how do we decide E and F? So what we can do is now go to the next isotope, Br81. Do the same exact thing, right? And you're going to get 158 if I'm looking at structure E, which still matches one of the peaks. But now, if you do that for structure F, you're going to get 160, right? 160. We don't have 160, right? So because we do not have that, that should tell you that F is not your answer, okay? So be very careful, all right? So it's a good idea to maybe you try both isotopes just to make absolute sure. So the answer in this case would be E, all right? And so that is how we do the mass spec questions. I hope this helped you guys out. If you have any questions, please feel free to email me, talk to a TA at the CLC. If you're watching this on YouTube, maybe leave a comment so that others who have a similar question can also see it. This will be the last video I will record for exam 2 of for your exam 2. I wish you guys luck. I'm sure you will do great. Your exam 1 average was really good. From what I've seen, you guys know what you're doing. All right. So good luck. Don't stress. Remember to just take your time and breathe, and you'll do fine. All right. Good luck, guys.